Good day and welcome back for part 2 of our discussion on tangents and velocity. The point of this section is to motivate and see how limits can arise naturally. And in our previous example, we saw that limits naturally arose when we were trying to find the slope of a tangent line. And in this video, we are going to explore a second example to see where limits can arise naturally. So the example is as follows. A ball is dropped from an air balloon, so we think somewhere really high. What we would like to do is find the instantaneous velocity of the ball after it has been falling for 5 seconds. And immediately you probably note we need some type of kind of function to work with here. And if we go back to an observation that was made by Galileo, we can note that there is a function s of t, which is 4.9 t squared, and this is a distance function. It's going to tell us how far the ball has fallen after t seconds. So this will tell us how many meters the ball has fallen after t seconds. And this may be a familiar formula you have encountered in past physics type courses. Now, the question becomes, how can we use this distance function, which tells us in a sense how far the ball has traveled, to determine what we want to calculate here, the instantaneous velocity? And the idea is very similar to what we encountered in our first example. We don't have enough information to calculate the instantaneous velocity all at once in, say, a single quick efficient step, but what we can do is hopefully approximate it as closely as we would like. And we can do that by determining average velocities. So let me give you just a quick reminder. We think of an average velocity as being distance over time. And this is something we are all very familiar with. For example, if we were to travel 100 miles and it takes us 2 hours, we would all immediately say, oh, we averaged 50 miles per hour. Now in this case, what we are interested in is the instantaneous velocity at 5 seconds. So what we are going to do is make a table of data where we're going to look at intervals around 5 seconds, and we're going to let that interval shrink so we get an average velocity on a smaller and smaller interval, about 5, which will hopefully give us some intuition as to what the instantaneous velocity should be. So we have an interval and an associated average velocity. So we'll look at the intervals where the time is from, say 5 to 6 seconds, so maybe starting off a bit larger than we need. And then we'll go from 5 to 5.1, 5 to 5.01, and then finally 5 to 5.001. So these are kind of intervals shrinking down to just that 5 seconds we are interested in, and we're shrinking down to it on the right side. And for each of these intervals, what we need to do is calculate out an average velocity. So if we want the average velocity on this interval from 5 to 6 seconds, so I'll say the average velocity is going to be given by, and remember we're thinking roughly distance over time. So I think the time part is maybe the easiest to see. So on this interval, how much time has elapsed? You take the larger value minus the smaller. So this would be time. But on the top here, we need kind of distance traveled. And this would be distance traveled between 5 and 6 seconds. And how we would calculate that is we would see how far we've traveled in total for the first 6 seconds. And we subtract off from this the part we don't want, the distance traveled from 0 to 5. And just to make that top as clear as possible, let me try to illustrate this with a picture. So if the object, is falling, say we have our ball down here, and we started off at time 0, and this is where we are at time 6 seconds. So that total distance would be s of 6. So how many meters the ball has fallen after 6 seconds. But that calculates way more than we want relative to this interval from 5 to 6. So what we have to do is kind of chop off the portion that we don't want. That is, we subtract away the s of 5. So maybe at 5 seconds, the ball is here. So if we were to remove this distance, what is left over from time 5 to time 6 is the desired distance. So that quantity that we have to subtract off would be the s of 5. In terms of our function of interest, if we substitute in these values, we would have 4.9 times 6 squared minus 4.9 times 5 squared over 1, and this is equal to 53.9. And note, this is the perfect scenario when we're getting a table of values to use something like a calculator. So the average velocity on this first interval is 53.9. And note the units are going to be meters per second, but I'm not going to write that for each of them. And then if we were to do these computations over and over again, we would have 49.49, 49.049, and if we did it on this last interval, 49.0049. And the observation that hopefully you are making is as this interval shrinks down to be closer and closer to 5, those associated average velocities appear to be approaching something. And what they appear to be approaching is 49. And let's just make a note so that we are all on the same page. The instantaneous velocity, so that's the velocity at an exact instant in time. Think maybe what your speedometer on your car tells you. The instantaneous velocity is what we will refer to as the limiting value of the average velocities. And with that in mind, we'll go ahead and we will say that the velocity at time 5, and this velocity at time 5 is referring to the instantaneous velocity, is going to be equal to 49 meters per second. So once again, we see another example where this idea of a limit arises very naturally. And before moving on, let me just note, as I know some of you might be wondering, this table of data that we've made, we've kind of looked at what's happening at intervals, with 5 being the left-hand endpoint. So we're kind of letting those intervals shrink down to 5 from the right. If you were to do the same thing from the left, you would also find that you're approaching this 49 meters per second. Now, to finish up this discussion on tangents and velocities, I want to note that there is a very natural connection between what we saw in our previous example, that is calculating the slope of a tangent line, related to finding this instantaneous velocity. And in order to see this connection, let me just graph this function s of t. So s of t is 4.9 t squared. So roughly speaking, if I'm just going to try to sketch this for positive values, we start off at the point 0, 0, and we have a kind of generic parabola opening up as we move to the right. So this would be the graph of s of t. And If we were to look at a few key points, so we were finding the instantaneous velocity at time 5. So on this graph, we have a point corresponding to time 5. So we have 5 comma, and I'm just going to leave it in this unsimplified form. And we were looking at average velocities. So for example, if we went up to time 6 and found that corresponding point, and we draw the line through those 2 points, note that this secant line that we've drawn, the line in red, its slope is going to be the average velocity. So the key observation to make is that average velocity, as we've calculated it above, is the slope of a secant line. And note, in terms of our first example in the part 1 video, MPQ would have been S of 6 minus S of 5 over 6 minus 5. So this slope of the secant line is exactly the formula we used to find the average velocity on that interval from 5 to 6. And if we take this one step further, what this is telling us is that the limiting value of the slopes of the secant lines, i.e. the slope of the tangent line, is going to be the instantaneous velocity. So the instantaneous velocity at time 5, just to make it in terms of our previous example, is the slope of the tangent line at t equals 5. So even though these examples were seemingly unrelated, note an instantaneous velocity is a slope of a tangent line. So they are very much related, and they both show us this natural way in which a limit arises. And that is where we will pick up in our next section. So stay tuned and take care.